Welcome to the final part of Lecture 4. We've seen in the previous part of this lecture how to get dimensionless groups by developing some insight, by looking at the physics of a problem and by saying, well, there's inertial and viscous stress at play here, there's got to be a Reynolds number, for example. What we're going to do in the final part of this lecture is use a first principles method to determine what dimensionless groups are present. Now, this can be quite long-winded, and I would recommend that this is a method of last resort. You should always look to form groups through physical intuition, through property ratios, maybe through Bernoulli's equation, and certainly by reference to page 35 of your data book. However, it is important to know how to form dimensionless groups from first principles, just in case you find yourself in a situation where all the other available techniques don't work. Now, on your example sheet, there is only one instance where you have to use a first principles approach. You might be told to use a first principles approach for some problems, just to practice a technique. But in reality, there is one part of one question where it is absolutely necessary. So, what we will do in this part of this lecture is to set up a problem and forget our insight. And we will blindly work out what property ratios make dimensionless groups, and then after we've done that we'll examine them to see how we could have done the problem more efficiently. So let's start by thinking about a problem that we haven't seen. Let's say I have this problem as I've drawn on the whiteboard. So on the whiteboard I have a particle submerged in a fluid, and I am pulling that particle with a certain force. What I want to do is to determine what force is required to pull that particle with a given diameter at a certain velocity through a liquid that has a density and viscosity associated with it. So it's in effect a drag problem. Now, using your insight on page 35 of the data book, you will be able to find two groups very quickly that we can use to solve this problem. But we're going to forget our insight. So we're going to break this process down into a number of steps. Step one is to say, right, we want to find force. That force has to be a function of the other parameters in the problem: velocity, diameter, density, viscosity. Okay, fine. So what I'm going to do is write a table of what units and hence what fundamental dimensions are associated with each of my parameters. Force. There we have force in newtons. We know that force is mass times acceleration, so we can work out from that the fundamental dimensions of ml over t squared. Velocity, meters per second, that's straightforward to write down as L over t. Diameter is also straightforward to write down, just taking fundamental unit L. Density, again, is similarly straightforward. It's kilos per cubic metre. Those are both fundamental units in their own right anyway, m over L squared. Viscosity. Right, now viscosity's SI unit is Pascal second. Pascal, we know, is newtons per square metre. So Pascal second is newtons per square metre per second. So we already have an expression for newtons, mass times acceleration. So we divide by m meters squared and multiply by seconds. And so viscosity takes fundamental dimensions m over lt. So that is step one. Write a table down, derive what the fundamental dimensions are for each of your parameters. Right, step two. What we're going to do is say, right, I need to find a relationship between F and everything else. So I'm going to say that my force F is equal to a numerical constant C, which is dimensionless, multiplied by each of the parameters in my problem raised to their own individual index. So F equals C, dimensionless numerical constant, V to the alpha, D to the beta, rho to the gamma, mu to the delta. Now I've written that down, let's substitute the fundamental dimensions for each of these parameters. So on the left hand side we have ml over t squared, on the right hand side we have L over t raised to alpha, L raised to beta, m over L cubed raised to gamma, m over Lt raised to delta. And I know that across an equal sign the dimensions have to be the same. So if I look at the indices of each dimension on the left-hand side, m, l and t squared, I can use that information to work out something about alpha, beta, gamma and delta. So let's do that. I've coloured each of the fundamental units here a different colour. Mass is blue, length is red, time is purple. Let's start off by examining mass. So on the left-hand side, mass has an index of 1. On the right-hand side, it has an index of gamma plus delta. Now that's one equation and two unknowns. I'm going to arbitrarily choose to write everything in terms of delta. So gamma now is 1 minus delta. Let's have a look at time in purple. On the left-hand side, it's in the denominator and it's squared, so it's index minus 2. On the right-hand side, time appears in the first and fourth group. So minus 2 equals minus alpha minus delta. Again, rewriting this in terms of delta, alpha equals 2 minus delta. That leaves us with length. Length appears in all the groups on the right-hand side, which is why we're looking at it last. It has an index 1, however, on the left-hand side. So alpha, we know is 2 minus delta. Beta, we haven't found a term for yet, but we'll be able to do so. Gamma, well, that's 1 minus delta. And delta is, of course, delta. So now we can figure out what beta is. So we started with saying f is a numerical constant c multiplied by a product of all the rest of the parameters raised to their individual indices. We have found we can relate all these indices now to the index delta, leaving us f equals c, our constant, v to the 2 minus delta, d to the 2 minus delta, rho to the 1 minus delta, and mu to the delta. That's step 2 complete. So here we have step 2. Now, when we divide by a group of terms that we choose, let's choose rho v squared d squared, put delta to 0, we should form dimensionless groups. So f over rho v squared d squared is dimensionless. Mu over rho vd is also dimensionless. Now mu over rho vd hopefully you recognise as being 1 over the Reynolds number, which we could have arrived at immediately. F over rho v squared d squared is less straightforward, but I invite you to look at page 35 of your data book and at a parameter called the drag coefficient, CD. You will see that our drag coefficient is written in terms of an area, and we can write the drag coefficient in terms of something that looks very similar to that group of terms that we've just derived. So what we have is a relationship between the drag coefficient and the Reynolds number, but we found that out from first principles. Fine. Okay, so step 3, divide through, make the equation dimensionless. Right, we're not quite there yet. What we've said is that my drag coefficient is now a numerical constant c, multiplied by 1 over the Reynolds number raised to a power delta. However, anything across an equals sign has to have the same dimensions. In this case, it's dimensionless. So on the right-hand side, there is no logical reason why I can't add together multiple terms that are c times a reciprocal of a Reynolds number raised to an index, with c and that index differing. So, strictly speaking, my drag coefficient is a sum of terms C1, 1 over Reynolds to delta 1, plus C2, 1 over Reynolds to delta 2, plus C3, 1 over Reynolds to delta 3, and so on and so forth. And we really don't know on the right-hand side whether there is just one term or a whole series of terms. Dimensionally, it's correct in either sense. Dimensional analysis has taken us as far as it can. What we need now is some experimental data to use this hand in hand with. So let's recap a few key points. We have derived some dimensionless groups from first principles. We've seen that it can be arduous and lengthy, and where it is pragmatic to do so, please use your intuition, insight, and page 35 of that data book. Use this first principles approach as a last resort. Remember, there is one part of one question on your example sheet where this approach is an absolute necessity. We've seen that dimensionless groups can be related by a series expression. So in this case we said that drag force isn't necessarily just numerical constant 1 over Reynolds to delta. Since the right hand side is dimensionless, there's no reason why we can't add multiple constant times 1 over Reynolds to an index together. And in order to determine what the final form of a relationship actually is, we need access to experimental data.